Buenos días a todos. Me confirman, ya estamos en vivo, ¿cierto? Muy buenos días a toda nuestra audiencia. Hoy en el canal de la Facultad de Ingeniería de YouTube tenemos el gusto de tener la cátedra Kimberly Clark 2020 de la Sociedad Internacional de Medios Porosos con la profesora Berly Knut. Para todos, el capítulo Colombia Interpor está teniendo sus inicios. Es la primera charla que tenemos en este marco. Con el apoyo del doctorado en Ingeniería Civil de la Universidad Nacional de Colombia, el cual ya está cumpliendo casi 10 años desde su apertura, estamos trayendo esta conferencia con este tema tan importante como es el de conocer, el de descifrar esos procesos a escala de poros de los geomateriales. La profesora nos va a mostrar una conferencia muy interesante en cómo esos procesos físicos, químicos y biológicos tienen un efecto en el paisaje terrestre y cómo los podemos ver analizándolo a partir de estos ensayos modernos que ella nos va a mostrar el día de hoy. Para darle una introducción a la profesora, le voy a dar la palabra al profesor Carlos Moncada, director del Departamento de Ingeniería Civil.
Buenos días a todos, muchísimas gracias por esta invitación y por asistir a esta conferencia. La doctora Ferli Gnude recibió su doctorado en geología en el año 2005 en la Universidad de Ghent, Bélgica, donde ha sido investigadora y profesora desde el año 2010. Ella es la team leader del proyecto Pore Progress, que es el Pore Scale Processes in Geomaterials Research Group, del Departamento de Geología de la Universidad de Ghent. Es una de las coordinadoras del Centro de Expertos en Tomografía y Rayos X de la Universidad de Ghent. Es una de las cofundadoras del ICGW spin-off, es una compañía llamada In-situ Matters, que más tarde fue fusionada con la compañía spin-off XRE y que ahora es parte de TSCAN. Ella se especializa en imágenes no destructivas de geomateriales y tiene un largo expertise en el uso de imágenes en tiempo real y de procesamiento de imágenes de espacios porosos. La profesora Nude ha publicado más de 100 artículos en journals, es actualmente la Chair of the Proposal Review Committee PRC del Tomcat Bin Line. Es una de las cofundadoras de Interpor Benelux y fue elegida como miembro del Consejo de Interpor en el año 2019. Es nombrada como profesora titular en el grupo de Hidrogeología y Medio Ambiente de la Universidad de Utrecht y trabaja en el campo de imágenes para medios porosos. El título de su presentación será Unraveling Pore Scale Processes in Geomaterials. Una vez más, bienvenida, profesora Gnude. De verdad es un honor tenerla en el Departamento de Ingeniería Civil y Agrícola de la Universidad Nacional de Colombia y muchas gracias a Leonardo por esta invitación. Adelante con su presentación, muy amable.
Ok, la presentación será en inglés para todo el mundo para que lo tengan muy claro. Professor Berly, we are ready for listening to you.
Okay, gracias for the nice presentation, introduction. Okay, I will share my screen. Continue. Yeah, should be okay. Do you see me?
Yes, we are seeing.
Okay. Okay, so my talk today will be about unraveling pore scale processes in geomaterials. And when you talk about pore scale processes in geomaterials, this could be a topic related to many things. Could be reservoir rocks, could be soil material. But what I will talk about today, or I will take this as a lead to my journey is weathering of rocks. And if you look to weathering of rocks, this is a combination of physical, chemical, and biological weathering. And so a lot of processes are playing a role there when studying weathering of rocks. And when people study this in lab or want to understand or predict behavior, what they typically do is they go to a quarry or an outcrop, or if they study cultural heritage and monuments, they go to a monument and they do first macroscopical observations. After doing that, they typically take samples, they go to the lab with them, and then they do a series of tests. This can be identification tests using optical microscopy, scanning electron microscopy, to characterize the minerals that are present, to characterize the structures. People also do performance tests to see how the stone behaves, like compressive strength test, tensile testing, checking the pore size distribution with mercury intrusion porosimetry, calculating how the capillary water uptake is, or how the drying rate is of a rock, because fluid flow has a big impact on weathering behavior in this case. And then in the end, if people want to have an idea about the durability of a rock, they will monitor this using lab infrastructure by following specific standards, and using climatic chambers. They can mimic in a fast way, for instance, a series of freeze thaw, or they do tests to study salt weathering in order to have an idea how the rock is behaving related to this. However, if you look what you're studying in lab related to durability and what you see in reality is not always the same. And the reason for that is that, of course, you have a high variety of changes in geochemical structure and about the rock itself, because it's a heterogeneous rock. And then you have also a difference in the processes. And this is because in reality, the way the environment is changing, for instance, going from over day at a certain temperature to night, is a different speed than when you are using a climatic chamber to fast mimic those cycles. And so because you are having other changes in speed of difference in relative humidity or temperature, you are also stimulating other processes. Also, in reality, rocks can be not fully saturated or semi-saturated, and in lab you often determine one specific condition to be able to compare everything to each other. So this is challenging, and if you want to be able to predict or understand the macroscopical behavior, what you really need to have is you need to have insights in the 3D microstructure and the 3D chemical composition. And you also need to know the 3D dynamical processes that are playing a role, because what is happening on the pore scale influences the macroscopic behavior. So we need, in reality, integrated experiments where we can look inside the material in a dynamic way at high resolution to be able to visualize the pore scale processes. And that is why we use X-rays. And X-rays were discovered by Röntgen in 1895, for which he got the Nobel Prize. And the power of X-rays is that, unlike visible light, they can penetrate matter. So therefore, they are ideally suited for internal inspection of objects. And what you measure with X-rays, or what you see in X-ray radiographs, which you are probably familiar with when your arm is broken, also an X-ray radiograph is taken. It depends on the density and the average atomic number of your materials in question. So if there is a difference, then you will have contrast in your radiographs. So depending on the difference in composition of your materials. So if you do X-ray radiography, you need an X-ray source, you need an X-ray detector, and in the middle, you have your sample. So because this gives an information about 3D information on a 2D detector, there was a new development. And this was in the late 60s, early 70s by Cormack and Hounsfield, who developed the first CT scanner, also known as a computed actual tomography scanner or a CAT scanner. They also got a Nobel Prize for medicine, and this is also something you might be familiar with. This is the medical scanner used in a hospital to look, for instance, to your body in 3 dimensions. And then typically as a patient, you're laying down on the table and a source and detector are rotating around you. So the early developments were mainly focused on medical diagnostic imaging, and it is by the end of the 70s, 1970s, that first applications of CT in an industrial environment are being published. So what is the difference? For X-ray tomography, you also need an X-ray source and you need your X-ray detector. Now the difference is that instead of taking one radiograph, you take a series of radiographs over the different angle of the sample. So in a medical scanner, it is the patient that lays down and it's the source and detector rotating around the patient. While if you're examining materials like rocks, there is no problem in rotating your sample and keeping the X-ray source and X-ray detector stable. So, and you take a series of radiographs. And what you measure as intensity in your detector depends on the intensity of which is coming out of your X-ray source, and then is depending on the interaction of the X-rays with your material. And this is depending on the sample size. So the thicker your material and the longer the X-rays need to penetrate, the less intensity will come out. And also it's depending on the chemical composition. So the higher the average atomic number and the higher the density, also more X-rays, less X-rays will come out your sample. And so, okay, if you now have a series of radiographs, how do you come to your 3D image? And this is demonstrated here in a simple way on the left. This is by using filter back projection. This is software that you use to put the signal that you have from the series of radiographs into 2D and then finally 3D volumes. So if you look on the left, you see an X-ray source, you see the signal that is retrieved by the X-ray detector, and in red you see your sample. So your X-rays, they go through your sample and you get a certain signal at this location. Well, if you do this over all the angles, you have a series of signals around your sample. And then with back projection, you back project the information. And by doing so, you are able to more or less reconstruct the original object virtually. They apply a filter in order to have sharper edges. So that is the basic principle, or one of the principles that is used to come to a reconstruction or a virtual reconstruction of the original scanned image. So if you have a stone that you scan over different angles, your raw data is a series of radiographs. And then if you apply filter back projection, you are able to virtually reconstruct one slice, but in reality, you have the entire volume scanned. So you can have all the slices of your sample. And with X-ray CT, the resolution in X, Y, and Z is the same. And then you can virtually render this volume into a 3D object. So after scanning, you have your virtual rock available at high resolution. So if we go back to our rocks and our stones, if you go on the field and you take samples in the order, in this case, these are rocks. This is a sandstone, a Belgian sandstone, where you can clearly see macroscopically fractures appearing. And on the right, you have this same sandstone where you see layering of iron-rich layers, which are visible, of course, with the naked eye. But if you would scan this in a medical scanner, and these are blocks of 5 by 5 centimeters in size, you can immediately virtually cut this open and see the different fractures. And what you also see here is you virtually see the different layers because there is a contrast between the quartz rich zones and the layers which are iron richer, and so having a higher attenuation for X-rays, and therefore they are brighter. So you can virtually cut it open and look to the internal structure of your rock. However, if you have a sample, this is a sample of, let's say, 1 centimeter diameter, the details are not high enough to say something about the pore scale processes. So we need higher resolution. And that is why we use micro CT scanners, where we can go for higher resolutions. So here you have an overview of, and you see immediately that depending on the diameter of your material, we have another voxel size. So here we have a sample size which is rather big, 40 millimeters diameter, where the voxel size is 13 micron. Here we have a micro plug of 5 millimeters diameter and voxel size is 5 micron. And here we have a 2 millimeter micro plug with a voxel size of 1.8 micrometer. So you see that there is a link between sample size and resolution. And this is because resolution is depending on the sample size. So what is influencing the resolution of a system? That is the focal spot of your X-ray source, the resolution of your detector, and the magnification that we're using. And the magnification that we're using is depending on the distance between the X-ray source and the detector, and the distance between your X-ray source and your object. This means that if you have a smaller sample, well, depending on the sample size, you will influence the resolution. So even if you have a machine bot, which could reach resolutions up to, let's say, 800 nanometer in theory, that is possible. That's no problem with the micro CT system, but that will be under the ideal conditions that you're also working at the maximum magnification. And this is then related to the sample size, but also to the composition. Because if you are dealing with a big sample, let's say a rock, and it's big, what you want is that during rotation, it remains in your field of view towards the detector. So if it is a big sample, you will position it much further away from your X-ray source, having a lower magnification, and therefore also having a lower, well, not so high resolution. Another aspect is that if you are having very dense materials, you typically have to use high energy. And by working at high energy, typically your focal spot also becomes a bit bigger. So you're influencing intrinsically also there a bit the resolution. If you have a small sample, you can put it closer to your X-ray source and therefore having a better magnification and therefore being able to see more. And that is immediately why when people are working with micro CT, most of the times the samples are rather small, or we try to find a balance with what is still okay in sample size and what is needed to see the processes. So that is an important aspect with micro CT. Here you see an experimental setup of a micro CT scanner. So at the Center for X-ray Tomography in Ghent, we have built several CT scanners. And this is an example of one of those X-ray CT scanners. So you see here two X-ray tubes, a nano X-ray tube and a micro X-ray tube. The different tubes have a different spot, a focal spot, so they are having also already an impact on the resolution of the system. But the nano X-ray tube is typically for light materials, while the micro X-ray tube is more for rock materials. And then we have rotation stage in order to have your sample rotating very smoothly. So it's air bearing, that during rotation there is no shift in or movement of the sample. And we have also a piezo translation stage in order to position our sample ideally in the center of rotation of the object. And then here we have two detectors in this case also. Well, Varian is more sensitive for higher energies. Photonic science is ideally for lighter materials, lower energies. So depending on what kind of sample we have, we then switch in X-ray source and in X-ray detector. This is all also there are also translation stages, and this allows us also to play with the distance between, for instance, source detector or source object. And this is then also positioned on an active vibration damping table in order to have no influence of movement around the setup that might influence the stability or during rotation, because everything needs to be as stable as possible. So in Ghent, we have our core business is a high resolution X-ray CT. We have built several scanners, and some of them I will come to in more detail during this talk. So because of the different scanners, we can scan a high variety of samples, sample sizes, but of course, bigger sample sizes mean a lower resolution and different compositions and different kind of materials. We are an open center which are helping academic and industrial people with their research or research questions. Okay, but if you want to study rocks, first thing what you would do is, okay, you want to have structural imaging and analysis, and therefore you need to have multi-scale 3D imaging, because when you're studying rocks, we all know that depending on where you take a sample or the sample size, that the characteristics will be different because it's heterogeneous. So normally when you study rocks, you will take thin sections. And here you have examples of three French limestones, Noyon-Fine, Savonnière, and Neuville, who are French limestones which are typically used as building stones also in Belgium and in the Netherlands and in France. So if you study those, you see immediately the structure. And if you are an expert in optical petrography, you have the possibility to determine the different minerals as well. If you take a piece of stone and you put it in a CT scanner, you see the results that you get on the bottom of this slide. So you see that we can immediately see the same structure. So that is no problem. And the benefit is you do not have to do any sample preparation. So that is a good thing. It's non-destructive. The only drawback is that based on these images, you're unable to identify the different minerals if you do not have prior knowledge, for instance. So a typical or a workflow that is possible is, for instance, taking a bigger sample, scan it at lower resolution, maybe have it polished so that you can combine it with some EDX or XRF. Depending on the composition, you can take subsamples for higher resolution CT and even go to other techniques which are even higher in resolution in 3D. Can be FIB-SAM or CSAX, for instance. So you have microplugs that you take, and then for instance, here you see that we can identify two zones of interest. You take then subsamples again, and then you have high detail where you can discriminate the minerals and the pore space, and you can, so you see immediately the different composition. If this is not enough and you need to have more detail, you can combine this with scanning electron microscopy, which is has a very high resolution, but in 2D, or you can go to focused ion beam scanning electron microscopy, which is also in nanometers resolution, but is in 3D. And for those who are not familiar with this technology, this is what you have, if you have your material of interest, with the focused ion beam, you remove some material, and then with the electron beam, you take a standard scanning electron microscopy image. And then with focused ion beam, you will remove a bit of the material and you take again a SAM image. And so by removing and then always taking a picture, you are virtually making a 3D data set. The drawback of this technique, of course, is that it's destructive and it only works for small samples, small material, small volumes. If you are studying dynamic processes, you do not maybe want to destruct your material and you're looking for an option where you can look inside your material at high resolution in 3D, non-destructive. And that is why we then experimented with coherent small angle X-ray scattering, or CSAX, in the Pore Institute in Villingen in Switzerland. There is a CSAX beamline where you can do where you can reach resolutions up to 60 nanometer in 3D non-destructively, and it provides also chemical information. If you look on internet, it's also called sometimes nanotomography, ptychographic tomography, or small angle X-ray scattering, of course. And what you do is you need to have a very small sample. You position it also on your sample holder. Your source or your source of X-rays is produced by the synchrotron, and then you have a detector. And this detector records a grid of overlapping diffraction patterns over many angles and registers your sample in a non-destructive way. Here you see the setup. I've put also always the references of this work on my slides. But as you can see, if you look on internet, you will see that also much more is being done with these kind of techniques. But a challenge was, for instance, to produce a small sample, which is, of course, challenging when working with geological material. For that, we originally tried to do this with a focused ion beam. Instead of milling a material away for having SAM images, we used the focused ion beam to mill material away in order to have a sample ready. So if we scan this, we were able to look in our case, and this was in results. This experiment was done, I think, in 2014. So voxel sizes that we then could reach were in the order of 34 nanometer, 17 nanometer. But we had in 3D the internal structure. We could even see liquids inside the pore structure, and we could even try to determine the contact angle. We could quantify the porosity. We could also measure expansion of clay minerals because it's non-destructive. So we could scan the material, then put it. You have the possibility to add a climatic chamber, for instance, around your sample, so you can control relative humidity and temperature. And then you can wait until everything is stable again, and then scan again. So we tested also the impact of wet and dry conditions on our sample, which was clay rich. And we did also chemical analysis. In our chemical analysis, we noticed that the liquid that we had in mind and what we were hoping for was water, turned out to be glue. It's a good thing because it proves that the system is working well. Of course, this was not what we originally hoped for. It was the glue that we used to put our sample on our sample holder in order to keep it stable. This is, it's an interesting thing to use depending on the scientific questions that you have. But you can see that the higher and higher you go in resolution, the smaller your sample gets. And that is, of course, a challenge for sure if you're working with heterogeneous material and you want to have something of a kind of representative volume that you're analyzing. So we are currently trying to see if we can try to solve this with another technique, which would work complementary. And this is based on the principle of X-ray grating interferometry. And this was published, for instance, by Matthias Callas in 2017, where he used interferometry, dual phase grating interferometry for tunable dark field sensitivity. And the idea is that with the grating interferometry, you are visualizing features that are below resolution. So when using gratings, you get not only X-ray absorbed images, you get X-ray refracted images, and you get X-rays that are scattered, which are called the dark field images. And it is the scattering that is due to features which are below resolution that we want to capture in order to say something about composition. So what do you need? You need to have those gratings. And here you see a setup where you have your X-ray source, your sample, and your detector, similar like your normal setup. But then you have gratings in between. And this is how we are currently developing the system to have it in our lab. But what was done in the past, most of the times was also done at synchrotrons. But of course, at certain locations, you are already finding systems with grating interferometry. And so you see here that you can move the gratings parallel to each other and perpendicular to each other. And depending on how you position them, you will get another signal. So depending on the movement, you will get the absorption signal, the differential phase contrast, and also the visibility reduction, or what is also called the dark field signal. And we try to do this first at the synchrotron, and the next step will be to do this in lab. And therefore we selected a roofing tile. Why? Because we know that there is research ongoing, but a roofing tile is very difficult to study with normal micro CT. And that's because we know that, for instance, this roofing tile has a porosity, an open porosity of 34%. We know that most of the pores are below 1 micron. And so if we scan this with our system, for instance, having a few millimeters of diameter, and we scan at a voxel size of 8 micron, we can only detect everything what is in black are the pores porosity of around 2%. If we take a much smaller sample, of around 1 millimeter diameter and scan again with another system where we can reach a resolution of 2 micron, you see that we can detect much more pores, like here in this case around 12%. But we know also that we are missing a lot of microporosity which is present and which is not visible because it's smaller than 2 micron voxel size. So we wanted to see, okay, with the dark field signal, can we say something about the presence of having pores available below that resolution? And so we did experiments last year where we took an absorption and a dark field image. And this is a nice example here, because you see here something which looks like a grain. And your question could be, is this a specific grain which contains microporosity, or is this a solid material with no microporosity? And based on the dark field images, we can say that here there are no micropores available, and that is like giving no signal. Similar for this area, for instance. While based on this image alone, you are not able to identify this. So we are now working on a method in order to be able to say, yes, this zone contains pores between 200 and 600 nanometers. This zone contains pores between 700 and 1 micron, 700 nanometers and 1 micron. And this zone contains no pores, something like that. So that's something we are working on closely in collaboration with Marco Stampanoni of ETH Zurich and Paul Schroeder Institute in Switzerland. Another important step is 3D chemical characterization. And one of the things people can do is combine X-ray CT with scanning electron microscopy by registration. So for instance, you have your rock that is already polished, you scan it with CT, you then put it under a SAM EDS in order to get the mineral mapping, and then you combine the gray values that you see on your surface with what you get from the SAM EDS signal. Another possibility is combining micro-CT with XRF. And XRF is an excellent tool also to obtain the missing information of the chemical properties that CT does not provide. So you also need an X-ray source, and then you are collecting the XRF signal, and this allows you to get chemical information. So what we did in the past was we took a sample, in this case a yellow rock, we scanned it with CT, we see different gray values, and these different gray values are related to difference in average atomic number and density. Then we did, this surface was put in another system where they do micro XRF. Therefore, we got mapping of all the elements, and then by cluster analysis, we were able to identify the minerals, which are biotite, magnetite, and zircon, and we were able to match then this signal with the gray values in our CT image, and then estimate how the distribution was inside our entire volume. Of course, this is based on a 2D superficial measurement with XRF, and then you estimate based on similar gray values. And of course, a bit of logic is also, of course, normal because you know the material. But this was the start of our new scanner where we combined CT with XRF. So this is our Heracles scanner where we have an X-ray source, and we have here two detectors, the photonic science again for light materials, a Varian detector for higher energy, and then we have two end stations for XRF. And this is all air bearing, this place. So the sample is first scanned, and then with software we say, okay, we want to have a point analysis at this spot, and then it automatically goes to one of the end stations. And so we have CT and we have the two end stations, and one of the end stations is specifically for X-ray fluorescence tomography with a focal spot of 20 micron, and the other end station is for confocal XRF where the focal spot is 10 micron. So higher resolution in this case, higher sensitivity, but the other one giving you the ability to do a kind of 2D chemical mapping. And so the benefit here is that you can first do a CT scan. You can say, okay, I want to have point analysis here or in this place, and then you can do the characterization. So you have the spectrum, and you can draw lines on your sample, and then you get the elemental information. And you can also do, like I said, a kind of mapping. And I tested this on a limestone where I added gold nanoparticles in, I think, on average 13 micron, 13 nanometer diameter. And I added them on my Savoniere. And then I wanted to see if this signal was picked up with the XRF. And in green, you see where the gold is present. For the rest, you see mainly calcite, which is logic, and also some iron concentration. You also see that in the middle, no signal is picked up. And that is because XRF mainly works from the surface until something around, depending on the element that you want to map, something around 200 micron in depth. So it's not ideal, but it's a way to complement the CT data with chemical information. So that is why we're also exploring other possibilities. For instance, what is called in literature color X-ray micro-CT or hyperspectral X-ray micro-CT or spectral X-ray micro-CT. And there you need an X-ray source, your sample, and instead of your normal X-ray detector, you have a hyperspectral or a spectral detector, which is able to get the spectrum of your sample. And in Ghent, we have two detectors, an SLCOM more sensitive for low energy and a Hexitech more sensitive for high energy. And we are currently in the framework of a European project exploring the possibilities there. So here you have, for instance, a sediment with a mixture, which is consists of a mixture between quartz, wollastonite, gold, and lead particles. And if you scan this, here you see the radiograph, and here you see one reconstruction. You see that you have brighter grains, and this can be quartz or gold or lead, but without prior knowledge, you are unable to say something about this. If you use a spectral detector, this is the image that you get, and you see that the image quality is coarser. This is because the resolution of the detector is lower, less pixels, but you get a spectrum. And this means that you can then identify, okay, in this grain, how does the spectrum look like? And it allows you to say, okay, this is tungsten, this is gold, and this is lead. So you can distinguish the difference based on the spectrum that comes out. So we are currently working on this in collaboration with Autotech, HZDR, and Tescon to see what we can do, for instance, for ore identification. And then if you have your material completely characterized, the next step is dynamic imaging, and therefore you need to have fast 4D imaging. So for the imaging, if you want to investigate dynamics at the pore scale, you need to have sufficient time resolution, because what you want is, if you have a process that you want to visualize, which takes 2 weeks in order to change, then there is no problem to do a scan on Monday morning and scan on Friday evening, and then the next week, and you will be able to get time-lapse scanning. But if you want to visualize something which is changing faster, let's say that it is changing in 2 hours, that means that with CT, you want that your sample is stable during rotation. So you need to have a very fast scan, for instance, which takes a few minutes. So you can scan the first few minutes, then after 20 minutes, then after 40 minutes, in order to visualize the process. So you need to have fast scanning. And normally this is done at synchrotrons, because what we do is with synchrotrons, you can have a high flux, and so you can have a high signal to noise ratio. So if you are working on using a synchrotron, you are able to do fast scanning. And so that is also what is typically done. And here I have a map of all well, you see that there are a lot of synchrotrons available where you can do experiments. But experiments are done on those synchrotrons. In order to have access there, you need to write a proposal, and you need to have beam time. And once you have beam time, you have maybe time for 2, 3, 5 days to do experiments, but then you have to go back. And that is not always ideal. So it would be good to have a system where you can do or time-lapse scanning to do something in kind of preparation, or where you can do experiments in lab in order to prepare yourself. But at the synchrotrons, at the moment, it's possible to do, I found this on Nature, 208 tomographies per second at PSI, for instance. So that means 208 rotations per second or scans. So that means that the process that you're imaging can be already very fast. But we try to find something in between, and that is why we developed our own environmental CT scanner for dynamic imaging. And the idea is that we have now a source and detect, well, the source is here, detector is here, rotating around our sample, because if we want to scan continuously, because with this system we can do continuous scanning of 20 minutes, at the full scan takes 12 seconds and the focal spot is 5 micron. But the thing is that if you want to have, for instance, flow wires attached to your sample, or temperature sensors, if everything is rotating for 20 minutes, this is also can be a challenge. And sometimes if we go for fast imaging, we do not, and if you're working with liquids, we do not want that our sample is rotating very fast. So then it's good that our source and detector are rotating. So this is our environmental CT scanner. And we have, of course, invested in add-on modules for in situ imaging. So to do tests on reactive fluid flow, climatization, where we can control temperature, relative humidity. We have freezing cells. We have also a commercial system where we can do compressive testing, tensile testing, control of temperature, and also capillary water uptake. And this allows us, using this scanner, to, for instance, study solute transport in limestone. So here you have an example of our rock where we started with, our limestone, and which was fully saturated with water. And then we inject a salt solution from the bottom, and you see in function of time how this solution is spreading in this water-saturated rock. And you see how the concentration is changing in function of time. So you can follow here each 12 seconds or each 4 seconds we reconstruct even, and you see how this liquid is slowly spreading and becoming we artificially colored this, of course, because in reality original images are gray scale, and you see how certain pores become more greener, and this allows us to visualize advection and diffusion and preferential flow paths and to study this. You do not only look at those images to see what is happening, but you can quantify a lot. So you can quantify the concentrations of your salt inside your pore. You can quantify how the relative concentration is changing in function of time. So you can say, okay, I want to monitor here this virtual pore. Of course, this is an open pore network where all pores are interconnected. But if you virtually classify them based on the pore throats and the pore bodies, you can distinguish them. And you can also determine, for instance, the arrival time of the salt in each pore and visualize this. Another thing what you can do is study salt crystallization. This is also an important factor in weathering of rocks. So you can, here on the left, you see a salt solution, which is going from room temperature to 0 degrees, and you see how a salt is precipitating in a capillary. And here we have a rock, a sandstone, which is saturated with a salt solution, which we made virtually in, color-coded in green. And then we let the sample dry out, and you can see how the flow is going from your liquid. And in red, we have the precipitation of your salt in function of time. And so you can follow this in detail. Because it's non-destructive, you can also repeat. You can make your sample wet again and make it dry again and see how the salt is migrating. And if you do this, cycles of wetting and drying, you will see that after a few cycles that the salt is not at the surface anymore, but is more precipitating internally in your rock, which might be a problem because it's salt precipitating at the surface causes aesthetical problems. Salt precipitating inside the rock can create pressure zones and can create fractures and degradation. So besides looking at this, one of the things that we do is if you have this kind of rock, we virtually, using pore network extraction, we virtually distinguish the different pores and the pore throats. We know for each pore the location, the dimensions, we know the pore throats. And then what we do is we virtually, in function of time, visualize how the gray values are changing. So if this pore, this blue pore is, for instance, filled with salt solution of a certain gray value, you can then visualize, okay, during drying, what is happening. If if it's drying out, the pore will become darker. if it is salt precipitating, it will become brighter because of the higher density of the salt. And so you can then start to follow, okay, in which pores with which equivalent diameter do you have drying out and no salt being filled, and how is this progressing in function of time? So here we see from the bigger pores to our smaller pores, while we can also see that the salt is being filled typically in the smaller pores and going slowly to the bigger ones. And this is then important for modeling the drying crystallization dynamics, for instance. So with CT in our team, we are studying rock weathering, like salt and ice crystallization, the effect of freeze-thaw cycles. We are checking the effect of an acidic environment and reactive fluid flow, and where do you get dissolution and precipitation of gypsum in rocks. We study also microbiological activity. So here, for instance, due to the precipitation of calcite induced by bacteria, you can see where the bacteria precipitated calcite. We study fracture behavior, so we are and try to link the behavior between the stone, the original microstructure, and then the pressure that is applied. And you can study any kind of fluid flow experiment with that. And we use this knowledge. One of the things where we use this for is for conservation of cultural heritage, but of course this can be used for many other things like CO2 sequestration as one of the other examples, or the way of solute transport inside reservoirs. So I now demonstrated all the possibilities that are currently possible to do the characterization, to visualize, and to image your processes. But okay, how do we come from this pore scale information to then what is happening on the field? And so one of the things we use is image-based pore network models. And so we use the CT data that we use to look for the processes also as input for pore network models. So you have your CT image, for instance, here on the left, and then we make a kind of representation of the pore bodies with red dots and the pore throats with cylinders in order to represent the pore network in a more simplified way. And if we are not able to get visualize the porosity below resolution, we add links which are with upscaled microporosity properties. And for more information, I refer to the article, for instance, of Tom Bultres on multi-scale based micro-CT pore network models. And so once you have this, you can start to model, for instance, multi-phase flow in rocks. And here on the left, you see you have a pore network model, which was extracted from this sandstone, this Bentheimer sandstone. And the model is, I will explain again. So what you have is the rock is in the model fully water saturated in blue, and then we inject a non-wetting phase coming from the right towards the left in red. And we model this, but we also validate the model with doing CT scans. So we have our sample, we have it fully water saturated. We made the water, in this case, virtually invisible, so you don't see the water now. And then we inject also the oil, which is displacing the water, and we are visualizing how this movement is happening. So, and if I go one step back, now you see here, this is what we modeled, how the behavior would be. And this is then also reality of a very small part, of course. It's not completely a copy, but it's from a similar rock. So we use CT to validate also the models, and we use CT to give input to the models if something in the models is basically wrong because of certain assumptions that we can validate by doing the experiments with CT. And so this brings me to the end, that showing you, I want to conclude by saying that I think even with CT, still a lot of progress is being made, but with what is currently possible in lab and what is currently possible at the synchrotron, a lot is possible. And still, what I was showing, you see some of the things are published already a few years ago. This process of development is continuously ongoing. And I think it's very important, if you're interested in imaging materials, that you follow this closely, because there is a lot of possibilities, and I only selected a few to tell you during this talk. And I think if you combine this with experiments in lab, you are trying to see what's happening, because you need also the lab experiments for bigger samples to have it upscaled. But if you combine lab infrastructure with imaging infrastructure, and you use this also by advanced imaging experiments and advanced imaging modeling, and you can also work in interdisciplinary way, because I think you need to have experts in imaging, you need to have experts in modeling, you need to have field experts. So you need a big group of people with different knowledge, but then you are able, I think we are slowly getting there, where we are able to come from the Pore scale to the lab scale and to the field scale. And I would all invite you to visit Ghent, to see our scanners and to see our nice city center and the buildings that we're having. And hopefully in better times, this will be possible again. So I want to end by thanking you for your attention. And I also want to thank, of course, my past and current members of the Center for X-ray Tomography, because what I was showing today, of course, is a work of an entire team and is not my own work alone, of course. So thank you. I will now stop sharing my screen. Yes. And I'm open for questions. Any questions?
Thank you so much for such an interesting presentation. We have some questions for you. Let me read. Okay. How to use this methodology to measure porosity on unconsolidated sediments? Is a sample of this type of rocks possible?
Yes, so for unconsolidated sediments, we use the same procedure. The only challenge that you have, for instance, if you are looking for dynamic processes, is that the sediments can change in structure and position itself during the experiment. Well, when you're working with rocks, this is good because your rock itself is more or less stable. But if you have sediments, you have no possibility, well, it's no problem to put them in a holder and scan them to identify the grain shape, size, to identify the different pores. And everything will depend on your maximum diameter of your sample holder in order to know which resolution you are looking at. So if your samples are, let's say your sample holder is 1 centimeter, that means that the resolution will more or less be around between 5 and 10 micron, probably depending on the system, but that also means that you are not saying something about pores below that resolution. So that is why we sometimes take bigger samples to quantify the bigger pores, and then take subsamples to go for the smaller and the smaller pores.
Thank you. We have another question here. Mauricio Garcia asks, thanks, Dr. Luke. You talk about a lot of micro and nanoscale properties. I would like to know, would you scale mechanical properties to a larger scale, like, for example, a rock slope?
So if I understand well, the question is, if you do experiments on small samples, if you can use this for larger larger interpretations of bigger structures.
Yes, something like
yeah.
a
So so indeed, this is something to take into account, that because you are working on smaller samples, that this can influence the behavior and the results. So we did there is one publication on this that we published related to compressive strength, because if you are going for smaller samples, you start to maybe interfere with the properties also. So this is something to indeed be careful with and take into account. But this is something we did at a certain moment, but it's not our specialty. I think you have teams, for instance, the teams in France, in the south of France, who are more working on these kind of mechanical behavior and CT. They are more specialists in that field.
Okay, thank you. So, Christian Garcia is asking, are you using artificial intelligence in the post-processing of the images? Are you using artificial neural networks? Are you using convolutional neural networks for image classification?
So at the moment, I haven't, but this is something we are currently also moving towards. So indeed, at the moment or in the past, the way we are working was scanning, reconstructing, having then a data set of images, and then trying to obtain quantification out of it. This is not the ideal way for sure if you are processing, if you have huge amount of data sets. So one thing what we are looking at is trying to see if we can get if we can combine, for instance, CT with other sensors so that we can collect a signal. Okay, now something happened of importance. For instance, if you're freezing a rock during ice crystallization, there is suddenly a small shift in temperature, and this indicates ice is now being formed. So if you use this signal as information to go back to your original images, everything before and after the event, that is helpful. So this is something we are working on. And the other thing is, of course, what you're saying, artificial intelligence. We are working more closely with image processing teams. I am a geologist in background, so it's not my specialty, but I think there is a large field of possibilities there that is coming closer together and will be also one of the things in the future that will be frequently done.
Okay, thank you. So Antonio Preciosi says, thank you for your very interesting presentation. What is the bigger tomography you can make with your equipment?
So the biggest sample, I guess you mean with my equipment, it depends on the sample composition. So if you have a limestone, which is mainly calcite and with maybe 30% porosity, there is no problem that the sample is in the order of 10, maybe even 15 centimeter diameter. If you are having a very dense rock with a lot of lead in it, for instance, it's for instance, ore material, then the thickness of your sample will be much smaller. So that is having an impact. But so typically, I would say we typically go for rocks in the order of 10, 15 centimeters maximum, up to 1 millimeter or even smaller in sample size. But you have other facilities where they are specialized in high energy. In Switzerland, there is a lab where they do high energy scans, where they can really do bigger things like motor blocks and have a source which has higher energy. But we are focusing something in between.
Okay, thank you. Mauricio asks, how difficult is to prepare a microsample for testing?
It depends what you want to see or do and what you want to test. and also for which equipment. If it is for CT and you just need to do a scan with CT, there is no difficulty. You just take a piece of rock and you put it on your sample holder. It just should not move during rotation, so needs to be fixed well. But that's the only thing. If you want to do start to do experiments combined with CT, then it becomes already more tricky, because if you want to do compressive strength, you want to have everything stable and perpendicular to the compression machine. For flow cells, you also want that sometimes the equipment itself is not maybe so difficult, but then air bubbles are entering in the system, which you don't want. So everything what I showed seems to be easy and fast, but often it was before a lot with trial and error, because sometimes these experiments also go wrong. So it's not that it is no problem and done always in very fast way. Otherwise, I probably would have shown much more 3D images of movies that we did.
Okay, thank you. Here we have another question. How could you upscale what you learned from a sample using these methods to estimate macro scale parameters like the hydraulic conductivity field?
Well, the idea is that we are using the CT to understand or to answer some specific behavior. For instance, if we are talking about flow, one of the things is contact angles. And sometimes in larger models, people assume that the contact angle will be a certain value. Well, if we do the experiments, we see that this is depending on certain parameters. And by doing this approach, we can get a better estimate of certain values, or we can see that this value is not a constant, but that it is changing in function of time. And this can then be implemented in the field models, for instance.
Okay. Here is another one. Sergio Garcia asked, what software do you use to simulate these flows?
To simulate the flows, I think, well, so the software that was used was it also based on the work that was done in Imperial College. So the work of Martin Blunt, for instance, we use typically these kind of approaches. We also use software like Aviso to render data, to look, to have certain specific details. So, and also there is some home in-house programming done by the postdocs to come to the results. But normally, if you look under our website, under our publications, you will find all details needed for specific questions.
Okay, so are you using thermo-hydromechanical chemical coupled models for flow, fluid, and transport modeling?
At the moment, no, not really. But this is also something towards the future where we will invest in, yes.
Okay, I think that there are no more questions here. No, we don't have more questions, so thank you so much for the time. Now, Leonardo is going to do some words.
Thank you very much, Burley, for your nice presentation, your nice talk. We see a lot of toys that you have on your lab to produce this interesting work. I have a final question. Do you think it is possible maybe to see for example, to produce a fracture on the rock? Because I see you are modeling the fractures maybe on a piece of work. I mean, I'm interested in modeling a piece of shale, and maybe we can produce a fracture, a small fracture, a micro fracture on the shale, and to see what's happening in this fracture and the processes associated to that.
Yes. So so if you use normal CT, it will depend on the dimension of your fracture width in order to be able to say, yes, there is something in it, or yes, it's opening or not. So that will be a challenging aspect. One way to verify this is maybe by introducing, this is something I haven't done yet, but I'm very interested in, is, for instance, introducing gases which are highly attenuating, which could fill in those original fractures, so you get contrast and it's getting brighter, and so you know, okay, it's present there. So this is after the fracture is made. If you another thing, what we are now looking for is to check if we can use the grating interferometry to say something about fractures, because for instance, we know at a certain moment with CT, we see, for instance, if we do freeze thaw, we see that during freezing at a certain moment, a fracture is appearing and then it closes again. But the first cycle, nothing is happening. But we don't know, is this because it's below the resolution or because there is no fracture? Because of the and the idea is to check if we could use the gratings to say, yes, something has changed below resolution, although we cannot, well, that we can get a signal with the grating interferometry. So this is something we are now currently working on, if this could be also an added possibility of using grating interferometry. But so yes, you can do this, but it also depends on which typical dimensions you are talking about and on which kind of sample size you need to have a representative sample. So this is the impact.
Thank you very much, for that answer and for the nice talk. In the name of Universidad Nacional de Colombia and the Interpore Colombia chapter, I will say thank you again for your nice talk, for sharing us all this research.
This was done with pleasure.
Okay, have a nice afternoon in Belgium.
Thank you. Thank you. Bye-bye.
Muchas gracias a toda nuestra audiencia por estar hoy en el canal de la Facultad de Ingeniería con la cátedra Kimberly Clark de Interpore, organizada por el Doctorado de Ingeniería Civil. Muchas gracias. Bye bye, Berly. Hasta luego a todos. Gracias.